Hey guys, this is question number 14 and let's see what we have to solve in this question. So in this question it is written a circular polarized laser of power P is incidence on a particle of mass m. The particle which was initially at rest completely absorbed the incident radiation. The kinetic energy of the particle as a function of time is given by these are the option. So what has been given in this question that a laser has been used as a external power source. Now the particle which was initially at rest and its mass m, it will absorb the energy from this laser light, and using this energy it will start moving. It will increase its kinetic energy. So it has been asked what will be that kinetic energy of the particle at time t. So to solve this problem, let me just first write how much energy this particle will absorb from the laser. So at time t, the particle will absorb energy from the laser is equals to be P into T, where P is the power and T times it will absorb the energy is equals to PT. So you can see here that the absorb energy is proportional to time. So if time is less, then absorb energy will be less, and since this energy will be utilized to gain the kinetic energy of the particle, so we can say that when T is less, the energy it will absorb from the laser that will be less, and because of that the velocity of the particle will also be less. On the other hand, when T will be large, this absorb energy will be large, so particle kinetic energy, or you can say velocity of the particle, will be very high. So depending upon this energy, at one times when T is very less, the absorb energy is very less, particle velocity is very less. And on the other hand, when time is large, absorb energy will be large and particle kinetic energy will be high, so velocity will be also high. And so using this, because of this time, we can solve this problem in classical limit as well as relativistic limit. So when T is very small, particle velocity will be small, so then we can solve this problem in classical limit. On the other hand, when T is very large, particle velocity will be very high, so we can use a relativistic limit. In between, when T is neither too small or not too high, then we can use approximate result, or you can say semi-relativistic approach. Semi-relativistic approach. So first we are considering classical limit. Classical limit. Classical limit. So when we will use this classical limit? When T is very small. When T is very small. When T is very small, absorb energy will be small, so velocity will be less, very small. So in this situation, we can use classical limit. So according to classical theory, how much momentum this laser will transfer to the particle at time t? Let me write that first. So the momentum that will be transferred to the particle by the laser in time duration in time duration t is small p is equals to, so the energy divided by c, energy divided by c, that will be that amount of momentum will incident on the particle, and since particle is going to absorb the whole radiation, so this amount of momentum actually transfer to the particle. So if you put the value of E, you have already calculated it, P into T divided by C. So this is the momentum of the particle at time t. So then according to classical theory, what will be the kinetic energy? Therefore the kinetic energy of the particle, is Ke is equals to momentum square divided by 2m. So if you put the value of phi here, then we'll get capital P square T square divided by 2m c square. 2m c square. So this will be the kinetic energy of the particle in classical limit, means when the time is very small. That time kinetic energy will be p square t square divided by 2m c square. 2m c square. So this will be the kinetic energy of the particle in classical limit. Classical limit means when t is very small. Okay. Now if we want to solve this problem in relativistic limit, so second case, it consider relativistic limit. So when we can use relativistic limit? When time is very high, time is very large. When time t is very large, then absorption energy will be very large, so particle velocity will also be very high. At that case we can use relativistic limit. So according to relativistic theory, the total energy of the particle is equals to, we can write rest mass energy mc square. M is given here rest mass, so m is the rest mass, m into c square, that is rest mass energy, plus absorb energy p into t. And also we can write this total energy in terms of kinetic energy and rest mass energy. So also we can write E is equals to kinetic energy, total energy of the particle is equals to kinetic energy plus rest mass energy. So in questions it is written rest mass energy actually m, so m naught will be actually m here, so mc square. So now if we compare these two equations, let's say this is equation number 1 and this is equation number 2. So if we compare these equations 1 and 2, then what we can write? We can write kinetic energy is equals to Pt. Kinetic energy of the particle is equals to Pt. So in relativistic limit, when time is very large, in that case the kinetic energy of the particle will be equals to P into T. P into T. Now if we want to solve this problem in another time duration, where the time is neither too small or too large, that time we can use semi-relativistic approach or semi-relativistic limit. So third case is Semi-relativistic limit. Semi-relativistic limit. Semi-relativistic limit. So when we can use that? When time t is neither too small nor too large. Nor too large. So in that case, we can use semi-relativistic limit. So in that case, E is equals to, again we can write m naught c square, where m naught is the rest mass energy. So in this questions it is written m. So we'll write mc square rest mass energy plus absorb energy, and also we can write E is equals to, in terms of total energy, in terms of momentum, if we want to write momentum, then it will be p square c square plus m naught square. Again m naught in this case actually m, rest mass energy. So we'll write m into c to the power 4. m into c to the power 4. So again, if I write, this is equation number 1, this is equation number 2. So from these equations we can calculate what will be the momentum of the particle. So for that, what we can write here, we can just equate these two equations. What we'll get? We'll get mc square plus capital P into T is equals to under root of p square c square plus m square c to the power 4. Now if we take square on the both side, then what we'll get? We'll get m square c to the power 4 plus 2 mc square into pt plus capital P square t square is equals to small p square c square plus m square c to the power 4. So now you can see here this mc square term will cancel out from both sides of this equation. So from here we can write the value of p square c square, and what will be that value? P square c square will be capital P square t square plus 2 mc square into capital P into T. This is the value of Pc, where is P? P is the relativistic momentum. Now if we want to calculate kinetic energy, therefore the kinetic energy of the particle is equals to total energy in terms of momentum. If we want to write in momentum, so we can write under root of p square c square minus plus m square c to the power 4 minus mc square, where m is in this case rest mass. M is rest mass. So now if we put the value of p square c square, already we have calculated here. So if we put this value here, then what we'll get? We'll get 2 m c square pt plus capital P square t square plus this term m square c to the power 4 minus mc square. Minus mc square, and then from this square root I am taking common m square c to the power 4. So when you take common of this term m square c square, so it will be if we write outside of the square root, so it will be mc square and then 1 plus p square t square plus 2mc square into pt divided by this term m square c to the power 4 whole under root, that is power half, minus mc square. So now if I this term, look at this term, if we take a binomial expansion of this term, and if we consider only first order approximation, then we can write mc square into 1 plus p square t square plus 2mc square pt divided by 2m square c to the power 4 minus mc square. So now if we multiply this mc with this whole term, with this bracket term, so what we'll get? We'll get mc square plus this 1 mc square will cancel out, so we can write p square t square plus 2 mc square into pt divided by 2 into mc square and then minus mc square, minus mc square. So again you can see here this term and this term will cancel out because the same. So now, so what we'll get here? Final kinetic energy, only this term. So from there we can take pt divided by 2 common. So if we take this term common, then what we'll get? pt divided by 2, then we'll get first term will give you pt divided by mc square, and then second term, this mc square will cancel out. Pt by 2 we are taking common, so this will give you plus 2. Okay, so under this approximation, so approximate result will get this answer. Okay, so in 3 limits we are getting actually 3 result. One is at relativistic limit, this is classical limit, this is a relativistic limit, and this is certain kind of approximation limit when time is neither too large or too less. So now take a look on the option that is given in this question. So here you can see this option C is given there. So option C will be actually the kinetic energy of the particle according to the classical limit. So if we consider classical limit, then we'll get what the kinetic energy of the particle will be pt square divided by 2mc square, which is given in question option C. And when you consider time is very large, that's the relativistic limit, and in that case the kinetic energy will be pt. But in questions it is not written here that t, what will be the value of t. T can be very small, t can be very large, or t can be in between them. So whenever examiner is not actually written anything, so basically we have to write, best way we can write the approximate answer, whether time neither too less or too large. So if we take this approximation limit, then in that case correct answer will be actually option A. Option A. So if examiner specify the situation where t is very small or if t is very large, then we can say we can solve this problem according to classical limit or relativistic limit. But if the examiner did not mention these things, that what will be the limit of time, so I think best way to take this approximation limit. So correct options will be option A. Option A. So thank you for watching. We'll see you in the next video.